The determinant would change, but the system on the whole, as a system of equations, would still have exactly the same solutions if they exist. And so we can also multiply one equation by some number, another equation by some other number, and add them, for instance, to eliminate some variable. That's what we did at school. For example, we did it also last time when we used Cramer's rule. We saw, for example, we could have, if we have an equation, I will write a small one, minus 5y equals 1, and 3x plus 2y equals 7, for example. Yes, what we did, we could, for example, multiply one equation by 2, the other equation by 5, and then add them up. And we would have 2 times 2 plus 3 times 5, that's 9 plus 15, 19x equals minus 10y plus 10y is 0, they disappear, and 2 times 1 plus 35, that's 37, so we can go on working. What we did, this is just an example. The purpose was, of course, getting rid of the variable y. So this is again something that is allowed in this method of elimination, because what we remember, the only reason, well, not exactly the only one, but the main reason why we use matrices is we have less to write. If every time we have to rewrite the whole system with all the variables, it's more to write than just copying the coefficients. And so once we have used these row operations to obtain the identity matrix on the left-hand side, what happens with this system is that the first row in this matrix means that 1x plus 0y plus 0z equals A. That 0x plus 1y plus 0z equals B. And 0x plus 0y plus 1z equals C, and we have the solution of the system. So in principle, Gauss' method allows, without even thinking about any determinants, to perform these row operations and obtain a solution. Of course, you might ask, so where's the catch? Why couldn't we do the same thing with the other two methods without any determinants? Of course, we have a catch, but we will have a look at that catch later. So at the moment, just let's move on to the next slide. And I think I have to erase this now. I have to clear this off. And let's have a look at some example. So in this case, okay, sorry, that's not what I had to do. Not what I wanted to do. All right, this is something that evidently has a slight problem with clear. No, it doesn't want to clear. What? Okay. So let's have a look at how we work with this. And so why did it show up? Okay. No, I don't need it. Okay. So let's try to create this system matrix. Okay, this is something that wants to show up all the time. I am writing, so it's 2. Okay, again. Right, I have, okay, this. So we have 2 minus 1, 5. We have 1 minus 2 minus 3, and we have 3, 4, 6. 3, 4, 6. And behind the line, we have 0, we have 4, and we have 7. And now let's try to perform these row operations with the matrix instead of equations instead of all these equations. Because if we do this with the equations, we have to write more. Here, the more is just like drawing a few lines. And so we could, first of all, evidently, a very good idea would be exchanging the first and the second equation. So I'm writing the sign of equivalence. This is equivalent to the matrix with the first and second row exchanged. 1 minus 2 minus 3 and 4. 2 minus 1, 5 and 0. And 3, 4, 6, 7. Okay. This is definitely more convenient for me to write on because I see clearly what I'm writing. Okay, so now let's do the normal thing, what we always do. Our thing is creating zeros below 1 because we want to make the identity matrix on the left-hand side, which means I want zeros below 1. Okay, so this means that row 2 minus 2 row 1 happens to be in the second row, and row 3 minus 3 row 1 has to be in the third row. Okay, not enough space on the right-hand side. My handwriting tends to be biggish. Okay, I lost something, sorry. Back. And so what, what we have, pen. What we have now is, let's see, we have, no, all right, I apologize. I keep losing my screen at times because this is the first time I actually am doing this, and whenever I place my hand somewhere where I shouldn't put it, it goes a bit wrong. So I'm coming back. Somehow is it this one? No, it's not this one. It's this one. Right. So I'm going on. Whenever I place my hand somehow in the wrong spot, things happen. And so I have 1 minus 2 minus 3, 4. Now I have 0. Minus 2 times minus 2 is 4. 4 minus 1 is 3. Minus 3 times minus 2 is 6. Added to 5 is 11. And 4 times minus 2 is minus 8. Minus 8 added to 0 is minus 8. And I have the wrong example showing. I'm very sorry. I will go back immediately. It's not this, and it's not this, and it's not this. Okay, I need to somehow find a system to do that. This is the one. Yes, I have to find a system to do these things properly, because otherwise I'm in trouble with my Android tablet. Okay, I lost the. No, where did this go? Oh, okay. I accidentally enlarged something. I still have to figure out how not to spoil my screen by placing my hand where I shouldn't do it. Okay. So now let's do with the third row. 3 minus 3 will of course be 0. Now, minus 2 times minus 3 is 6. 6 plus 10. 6 plus 4 is 10. And, okay, I'm very sorry. I keep pressing something wrong all the time, accidentally, by the way, without intention. And minus 3 times minus 3 is 9. 9 plus 6 is 15. And then I have 4 times minus 3 is minus 12. 7 minus 12 is minus 5. So now we see what we can do. We can divide, for example, the last equation could be divided by 5. Or it could be divided by 10 if we want to use it to make 1 in the second row. It's not so bad because when we divide something by 10, we get a decent decimal. It's not something very bad. So that's perhaps something that we could do. So let's just take 1/10 of row 3 and rewrite it. Let's exchange the two rows immediately so that we get 1 in the second row. So it's 1 minus 2 minus 3, 4. 0. Now 10 divided by 10, 15 divided by 10 is 1.5, and minus 5 divided by 10 is minus 1/2. And this is, okay, did I do it or did you do it? I think I did not. I think someone, No, it's fine. It's fine. If you learn how to work with me on the screen, I'll be very happy.
I'm sorry,
All right.
ma'am. It's me.
It's okay. It's okay.
Sorry.
It's okay. It's just part of the fun. It's part of the fun. We are all learning something. We are all having, let's say, actually, if you have fun, you learn better. I'm sure about that. It's just that I cannot make all mathematics fun. And this is the last row remaining. And now I can make 0 instead of 3, and that would require row 3 minus this 3 times this new row 2. And again, equivalent to the matrix as it is. 1 minus 2 minus 3. 4, 0, 1, 1.5 minus 0.5. And now I can have 0, 3 minus 3 will be 0. 11, 3 times, minus 3 times 1.5 is minus 4.5. 11 minus 4.5 will be 6.5. And minus 0.5 times minus 3 is 1.5. Minus 8 plus 1.5 is minus 6.5. See how nicely things work out. In fact, I can see actually that I have the last row divided by the 6.5. It's very easy. I have this already. So this means I have the Z value. This means I already have the Z value. Now I'm, at the moment, I'm rewriting the previous rows as they are. 1, minus 2, minus 3, and 4. In fact, at this moment, we could already say that now this system can be finished because I see that Z equals minus 1 from this. And now the next thing, I can take minus 1 instead of Z. So I can actually write that y plus 1.5 times Z, which is minus 1, is minus 0.5. And from there, I can immediately find the value of y. Minus 1.5, move to the other side, plus 1.5, so y will equal 1 from this. And finally, the x value, we can put y and z into the first equation, which we now see it's x minus 2 times y, that's 1, minus 3 times z, which is minus 1. So I have plus 1 here, has to be equal to 4. So these numbers, minus 2 plus 3, are from multiplying the coefficients, minus 2 and minus 3, by the corresponding variables, z values, and the z value for minus 3 times minus 1, and y value 1 for minus 2 times 1. So we can find the x value as well. So x plus 1 is 4, so x itself is 3. So we have the solution 3, 1, minus 1, putting things in the correct order. So this is how we can use Gauss method. This is an incomplete Gauss method. As you see in the top right triangle, we still do not have the zeros. So if we had the zeros, if we make zeros in the top right triangle, then we actually have the complete solution as it is. And in fact, we could, for instance, multiply the second row by 2. If we multiply the second row by 2 and add to the first row, we would in fact get the first row 1, 0, 0, and something. Well, 3 it would be. So this is in fact very possible to finish completely. So that's why I'm going to undo. No, I would better erase, I think, because this will work faster. So I could erase this and continue working a little bit. So this is one way that we could do it. And sometimes people are so impatient that when we see this triangular matrix, we say, okay, we can solve from bottom up, going upwards, we can solve everything. Everything is fine. So what I can do is, let's say, row 1 plus 2, row 2. And it gives me 1 plus 0 is 1, minus 2 plus 2 is 0, minus 3 plus 3 is 0, and 4 minus 1 is 3. But we did have that x is 3 already. We know that this is true, this is correct. And then we had this one row that was already good. And now to get rid of that 1.5, I could say, okay, let's take row 2 and subtract 1.5 row 3. So 0 minus 0, of course, is 0. 1 minus 0, of course, it's 1. 1.5 minus 1.5 is 0. And minus 0.5 plus 1.5 multiplying is 1. And now that's actually... there was very little that we had to do. Extra things, not so much extra. So from this, we also get the exact same solution. X is 3, Y is 1, and Z is -1. So if we manage to create, using Gauss method, to create all those zeros where necessary, we get the solution. And we didn't have to think about the determinant and singular metrics and the non-existent solutions. But of course, there's a big question. We might have trouble. We might have trouble with this. What kind of trouble? In what case would we get any trouble? That's something to be thought of. Please switch off your microphone, whoever hasn't done it. That's Vishnu. Okay, I will switch you off. If you don't switch off your microphone, I do. All right, so there we go. We have the solution, and let's see what next. And now, okay, let's move on. And I did not, I'm very sorry again. I forgot that I had to erase everything. Now, what about this? So we have this form in the identity matrix on the left-hand side and some numbers, ABC, on the right-hand side. This is called the reduced row echelon form. Why reduced? So row echelon form. So all these words, reduced row echelon form. So the row, because we are dealing with rows, we are focusing on rows more than on columns. That's why the word row. Echelon, what's an echelon actually, and why reduced? So the echelon form in principle means that we have this triangular type matrix. The echelon form, row echelon form, simply means we have a triangular kind of matrix. It could be a bigger one. It could be a longer one. It doesn't have to be 3 by 3. It could be 3 by 4, for example. But whatever matrix that has, let's say, zeros, 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 and then some other elements like this, is called a matrix in row echelon form. Row echelon form. Why echelon? Traditionally by echelon, we understand, let's say, an engine pulling a very long train of perhaps a cargo train, for instance, we might imagine. So echelon means that there's something, a leading coefficient, something that leads the situation, and then the rest that follows behind. That's the whole idea, this triangularity or trapezoid form, or sometimes a little bit crazier form if some elements are missing still. Reduced row echelon form means that the first coefficient in every row, the first non-zero coefficient in every row is 1. It also means that every main coefficient, we can call it the leading coefficient because it's the engine pulling the train, leading coefficient, because before that, we only have zeros. So every leading coefficient in every row, first of all, is behind the previous. It could be just in the next step, but it could be 2 steps behind. Anyway, every leading coefficient is behind the previous one. That's the echelon form. Next thing is every leading coefficient, if it's reduced, then every leading coefficient is 1, 1, 1. The leading coefficients are 1, and then the rest of the train, the right corner, is as many zeros as we can make in principle. Let's see how things go on. Okay, the next. Okay, so we have a problem. We will deal a little bit more. We will deal a little bit more about with the row echelon form later. So we have a problem if a row consists only of zeros. Then we have a problem. For example, we wanted to make this identity matrix. For example, let's take 4 by 4. I have no problem with 4 by 4. 0, 0, 1, 0. And then the fourth equation all of a sudden becomes all zeros. As we are trying to simplify the last row, all of a sudden, subtracting one of the other rows, we get 0, 0, 0, 0. So this would be a big problem, because that means that we cannot find the last variable. It's impossible to find. Again, there's more kinds to this problem. For example, we could have the last row consisting really only of zeros. See, notice this. 0, 0, 0, 0. What this means in this particular example, it means that on the right-hand side, we also have 0. So that would be 0x plus 0y plus 0z equals 0. What does this mean? This means perfectly nothing, because whatever x, y, z we would take, this would be true. So in fact, this last equation does not give us any information at all. No information at all. And in that case, the row echelon form would look like this. We do have some numbers here. We cannot eliminate one of them, because as soon as we try to eliminate one of them with the help of the other, we would spoil one of these zeros. So this is the best that we can do. So in principle, in the reduced row echelon form, above every leading coefficient, that is 1, above every leading coefficient, we only have zeros. So in fact, we might have some last columns like this. Last columns might be non-zeros if we have no way of eliminating these numbers without at the same time spoiling everything else. Another note immediately before somebody asks, we cannot do columns. We cannot do this with the help of columns, because remember, in an equation, we cannot simply add 3x plus 5y and say, oh no, this is 8y now. Of course not, because different columns now represent different variables. And this is the reason why in linear algebra, we basically focus on row operations, not on column operations. That's the reason, because we cannot mix the variables. X is X, Y is Y, Z is Z. In this case, we see we have infinitely many solutions. We will see how it happens and how to get those infinitely many solutions. It's not just any triplet of numbers works. No, not any triplet of numbers, but they will be connected somehow, of course. And then, of course, we have another possibility. Let's get rid of this and let's move on to the next stage. So the next case, infinitely many solutions was the first case. But now, if we do not have a zero, but if we have this kind of last row, what happens here? What happens here is that we have 0x plus 0y plus 0z equals some number, let's say 8, if c is 8, for example. What does this mean? This means there's contradiction, because this is impossible. This is impossible, so this means there are no solutions, because by perfectly legal and allowed transformations, we still have something that does not give us a good answer, or actually doesn't give us an answer at all, so something impossible. In this case, this means that this system is contradictory. A contradictory system not something that has solutions. So not consistent, inconsistent, or contradictory. And so we now know that the row operations, which row operations are allowed. We see in what cases we might have problems. And now the next part is, let's see how to deal with these problems. Because yes, of course, if there's no solution, we just write the answer, there's no solution, and that's it. But if there are those infinitely many solutions, we would like to see what they look like, what they are actually like. And so let's see, I think I have to erase this now. Yes, indeed. So I'm going to do that, clear. The next example, let's see how these things work out. So what we are doing, let's make this augmented matrix, 2, -1, 2, and 1. And the vertical line. Here we have no x, so the first coefficient is 0 already. 3, 1, and on the right-hand side, -2. And here we have 4, 7, 7, and -1. And now we have to work out what happens here. So looks like the first thing's very simple, row 3, -2, row 2, because if I subtract 4 minus 4, I will get 0 there. It doesn't matter at this moment that we do not have 1 in the first row, because in any case later we can divide the first row by 2 if necessary. But let us leave those division things, those extra transformations, for later. Let's do now something, the more obvious things. So 2 minus 1, 2, 1. 0, 3, 1, -2, and 0. So -2 times -1 is 2, 7 plus 2 is 9. 2 in the first row times -2 is -4, added to 7 is 3. 1 times -2 is -2, added to -1 is -3. Now, if you can see that 3, 1, 9, 3, they can be somehow eliminated. So row 3 minus evidently 3, row 2, to get rid of 9. Again, we don't have to worry about 1, 1, 1 on the main diagonal, because we can always make it later by simply dividing the row by that number. But what we see here is, okay, the first row is the same, 2 minus 1, 2, 1. Second row, 0, 3, 1, -2. Third row, 0, -0. 9 minus 9, 3 minus 3, and -3 plus 6 is 3. So in this case, we see that the last row represents an equation 0x plus 0y plus 0z is 3, which means this is impossible, so there are no solutions. No solutions for this example. So in example 2, we have no solutions because we get this contradiction. This is the simplest case. This is the simplest of them all. You try to eliminate, you try to make this triangle of zeros. You want to make this triangle of zeros, but accidentally or not accidentally, but the system is such that along with this 0, you have created another one. And so the whole row on the left-hand side has become 0, 0, 0 row. But the problem is that on the right-hand side, the number is not 0 by using the same transformations correctly. So this means there will be no solutions. And this example in practice it's finished. There's nothing else to do. No solutions. This corresponds to one of the situations where the system determinant would be 0. Because even though the coefficients change and the determinant value perhaps changes, the determinant would in the end become equal to 0. As we see, one of the rows in this determinant consists of zeros only. And I am talking about this part now. And you will see that the system determinant, because using the same operations, we actually use the perfectly allowed operations, they are perfectly fine for the determinants as well. So we would see that the system determinant is actually 0. And this is the reason why Cramer's rule with 0 determinant and inverse matrix rule with 0 determinant and singular matrix, so not non-existent inverse matrix, cannot give us solution, because sometimes there's simply no solution when the determinant is 0. So this corresponds to the situation when the system determinant is 0. And now we will move on to the next example, I believe. So I will clear this so that I can move on. And yes, there we are. Another example looks very similar to the previous one. Okay, let's have a look at what might be going on.
So if the determinant is 0, will the answer always be no solution?
It's one possibility. We will see another possibility, because the other possibility is infinitely many. So the determinant, if the determinant is not 0, it means strictly there's one solution, exactly one, unique. But if the determinant is 0, then the solution either does not exist or is not unique. So 2 possibilities for the 0 determinant. So let's have a look at this. So let's take the white, the yellow actually, and let's see. So we have 3, -2, 1, and 7 on the right hand side. 7x plus 1y plus 0z equals 18, and 1x plus 5y minus 2z equals 4. Always the first rule is make sure you put the 0 in the correct place. If you put the 0 in the wrong place in the system matrix, you will get everything wrong. Okay, now in this one, looks like we could, for example, exchange the first and the third equation to get that 1. So we could simply exchange these 1, 5, minus 2, 4. And then we have 7, 1, 0, 18. And then we have 3 minus 2, 1, 7. Now let's make, for example, 0 below 1. Let's make row 2 evidently minus 7 row 1 to make 0 instead of 7. And so we have the first row remains as it is, 1, 5, minus 2, 4. Second row, 7 minus 7 is 0. So 5 times minus 7 is minus 34 plus 1. Minus 35 plus 1 is minus 34. Minus 2 times minus 7 is 14. Plus 0 is still 14. 4 times minus 7 is minus 28. Plus 18 is minus 10. And to make 0 here, we have to take row 3 minus 3, row 1. So let's remember that we multiply the whole row, but the decision by what number to multiply comes only from the first elements, comparing the first elements, because we want to make the zeros there. But let's remember we have to multiply and add, subtract the whole row. So 3 minus 3 is 0. Now, minus 3 times 5 is minus 15. Added to minus 2 is minus 17. Minus 2 times minus 3 is 6. Plus 1 is 7. And 4 times minus 3 is minus 12. Minus 12 plus 7 is minus 5. So what we see, in fact, is now we can, for example, divide the second row by 2. So that would be 1, 5, minus 2, 4, 0, minus 17. Or we can divide by minus 2. Let's make it a plus 17. Let's make it a plus 17, divide by minus 2. So 14 divided by minus 17 is minus 7. And minus 10, divided by minus 5 by minus 2 is 5. Minus 5. No, 5. Divide by minus 2, so that's plus 5. Yes. And then we have 0, minus 17, 7, minus 5. So if we now simply add these, I get 1, 5, minus 2, 4, not touching it. Second row, I'm leaving as it is. You cannot eliminate both. When you add them, the sum goes into one line only. You cannot put them in the both lines. Both rows cannot become 0. As you add them and you see that they eliminate each other, it's only one equation that gets eliminated. One of them remains. So in fact, what I should have written there was row 3 plus row 2 goes into row 3. But row 2 is the tool. It remains as it is. But row 3 becomes 0, 0, 0, 0. So now what? Now we have this interesting situation where we don't know what to do, but to make the reduced row echelon form. This is row echelon form, simply the row echelon form. Because we have rows, we have the echelon, every next leading coefficient is behind the first one. So 17 is to the right of 1. But we do not have the reduced form. That is, we do not yet have the 0, we do not have 1 here, and we do not have 0 above that one. So I am dividing the second row by 17. 1/17 of row 2. And so I have 0, 0, 0, 0. I have 0, 1, minus 7 over 17, and 5 divided by 17. No hope. I have to do it. And the first row for now, the same. 1, 5, minus 2, 4. Okay. So yes, we do see that we might have infinitely many solutions. We don't know yet, because maybe the first and the second row are in contradiction. So it might be that the last row is all zeros, but we also get a contradiction above. Not often, but occasionally it might happen. So now my aim is to get the reduced row of echelon form. In the reduced row echelon form, I need a 0 here. I need this 0. So I am now multiplying the second row by minus 5 and adding up to the first row. So I will have row 1 minus 5 row 2. Okay. Try to, no, I will write it somehow more nicely. I will write it row 1 minus 5 row 2, and of course it goes into row 1 as always. And so we have the last row 0, 0, 0, 0, the last but 1, the second row 1 minus 7 over 17 and 5 over 17. And now the first row, 1 minus 0 is, 1. Then 5 minus 5 will be 0. Now, minus 7 over 17 times minus 5 is 35 over 17. That's, and minus 2 is minus 34 over 17. So this leaves us with 1 over 17 there. Because minus 2 is, I repeat, that's arithmetics. Minus 34 over 17, that's the 2, this one, that's 2. And if I add minus 5 times 7 over 17, that is, I am adding this number. So that's my reasoning. And instead of 4, so 5 times minus 5 is minus 25 over 17. 4 would be 4 times 17, 68 over 17, minus 25 over 17. So that will be 43 over 17. So now I have something like this. So x plus 1/17 of z equals 43/17. That's the first equation. The second one is now y minus 7/17 times z equals 5/17. So in principle, what I see, I can express x and y in terms of z. And this is what we do in this method. We will now say something a little bit strange, perhaps, but not so strange from the view of formal mathematics. So in principle, we say let z be any arbitrary constant. For example, c, that would be arbitrary constant, arbitrary constant. Which means we can choose whatever number for z. Then x, so we see then what happens is x is 43/17 minus c/17. So I will write it like this. And then y would be, as we can see from this, 5 plus 7c/17. So we have 5/17, but we also add 7c. And this is the solution. So in principle, we see that it can be, well, many different triplets of numbers. Actually, we have infinitely many solutions, as you can see. What kind of solutions, what solutions they are all dependent on what we choose for C. So let me see what happens in the next slide. I guess I will have to erase this. Yes, but I can erase this because you see what happens there. I have the same in green. I have exactly the same numbers as I had here. I have this part. I have this part here in the green one. So I will now erase the scribblings on the board. This. And rewrite whatever we have, and that will be again the same thing. So we will say let z equals some arbitrary constant, whichever number we like, any number we like, then dependent on that. Well, actually, I would prefer to write it upwards because I'm going upwards in the system. So I will write then like this. Then y is, it was -5. I'm sorry, it was -5. I guess I did it wrong in the previous. And so y is 7c minus 5/17. And then from there, going still upwards, I have x is 43 minus c/17. So this is called the general solution. As I wrote it. No, it was +5. I was right. So I actually made a mistake when writing on the screen. Not writing on the screen, but in the file previously. So this is the correct. I had it correct. That's okay. All right. So this is called the general solution. You see exactly this thing. But we always start from bottom going up. So particular solutions. For example, we can choose any values of c. If c is 0, we have a particular solution, 43/17, 5/17, and 0. That's one particular solution. If c is, I don't know, perhaps 9. If c is 9, we might get something nice. 43 minus 9 is 34. 34 divided by 17 is 2. 7 times 9 is 63. 63 plus 5 is 68. Okay, 68 divided by 17 is 4 and 9. For instance, or I could have, if c is minus whatever, I don't know, maybe minus 11. So now I would have 54 over 17. That's not a nice number at all. I would have 77 plus 5, 82 divided by 11, and I would have minus 11. It will not, yeah, I know, it would not be it, because if it's minus 11, then we have minus 77 plus 5, that's minus 72. Yes,
Excuse me, ma'am.
Yes.
Can you show me the set of equations generally, not the question in which the second equation consists of z is equal to 0, right?
Well, which part?
Example 3. In
Yes.
the question it is given. It's 7x plus y is equal to 80.
Yes.
Which means z is equal to 0 in that.
Where do you have 0 in where? Z equals 0, yes. But that was if you can switch, in the given matrix, which I had to erase, I did have 7, 1, 0. And then after transformation, this happens after transformations. This is what we had after transformations. In the given matrix, we had the row 7, 1, 0, 18. We had 0 for Z. But after transformations, this is what happens when we finish the transformations. That's why we are doing all those transformations, so that we can have this specific form. It does not mean that in the second equation, the Z coefficient is 0. Now, please switch off your microphone, because there's an echo from yours, whatever microphones. And we had this. And we had, no, this is the previous, this is already something else. This is already something else. And okay, we were here with the particular solutions. In other words, if we have a situation like this, where we have a row consisting only of zeros, and if we manage to create this reduced row echelon form, that is 1, 0, K1, some number A, 0, 1, another number B, and then 0, 0, 0, 0, like this. It means that in principle, we can choose the last variable, the last unknown, to be whatever we like, and then that means we can express x and y, the first two variables, using this. And this is called the general solution. The one that I actually here have circled or framed is the general solution. The general solution means a solution that works always and in general, no matter what the C value, what constant C we take. And then from the general solution, which is simply a set of infinitely many solutions, from this general solution, we can find specific particular solutions by choosing special values of C, whatever we like. Sometimes we have some conditions, and we might find actually the particular condition because the situation tells us C must be this or X must be this. What are the other two, for instance? If not, then in principle, we have the general solution. We can produce as many particular solutions as we want. Now I'm clearing this off and moving on to the next part. So what happens if the matrix is not square? This was the other problem with Cramer's rule, for example, and the inverse matrix rule. They only work for square matrices. And so what happens when the matrix is not square is, again, a big and important questions that we are. And so we have 4 variables, 3 equations in example number 4. So what can be done with this? We can basically see that a row of 0 coefficients may happen. If not, then we could also imagine that there is a row of 0 coefficients like here. 0, 0, 0, 0, 0, for example. That's nothing. It means nothing, as you remember. The complete 0 row means nothing really. So we can actually write another row in the matrix if we like. And then if m is less than n, that is, if we really have fewer equations than variables, so more variables than equations, then, and if the system is consistent, then we can find the general solution. If we do not get a contradiction, then we can find the general solution. In many cases, if there are too many equations and not enough variables, for example, 5 equations but only 3 unknowns, there's a very good chance that this system will be contradictory. It might be contradictory. But if the system is consistent, then we could find the general solution. Now I am clearing this and trying to do this. Let's try to do this now. So the matrix would be 3, 2, 1. Minus 1. Here you see that the variables are denoted by x1, x2, x3, x4, so that we don't have to use too many letters of the alphabet. And the last term is 5, the free coefficient, the free number. Next we have 4, 3, 5. 0. See, there's x3 is missing here, so we have to put a 0 here. 5 and 2, so we always need to pay attention. And yes, absolutely, the idea was completely correct. We have to pay attention to where we put the 0. The problem was, of course, that we transformed the matrix. We changed it, so the numbers moved around and changed. All right, so we have this system of 3 equations, but 4 variables. We still try to do the exact same thing. So the first thing seems quite reasonable, that we simply exchange first row and the last row to make 1 in the top left corner, attempting to do the same thing. We don't know how we will succeed because there are so many equations, but let's see what happens. We are working towards the reduced row echelon form, ref. And then we have 3, 2, 1, minus 1, 5. And then we have 4, 3, 0, 5, 2. Now let's try the row reduction. Let's make zeros below the first leading coefficient. Let's make zeros here, so we will have row 2 minus 3, row 1, to make a 0 instead of 3, and row 3 minus 4, row 1, to make a 0 instead of 4. And so we get 1, 1, minus 1, 6 minus 3. I'm trying to make it smaller, because I know that my screen needs to be bigger. So 3 minus 3 is 0. 2 minus 3 is minus 1. 1 plus 3 is 4. And minus 1 minus 18 is minus 19. And minus 3 minus 15 is minus 18. So there's a lot of arithmetics to be done, and you have to pay attention to many numbers at the same time. You have to be very careful. And now 4 minus 4 is 0. 3 minus 4 is minus 1. 0 plus 4, minus 1 times minus 4 is plus 4, is 4. 6 times minus 4 is minus 24. Minus 24 plus 5 is minus 19. And minus 3 times minus 4 is 12. 12 is 12 plus, do I have 2 there? Or did I do something wrong? Let me check just a moment.
Ma'am, how do minus 19 in second row?
19 minus 19. If I multiply the first row by minus 3, 6 times minus 3 is minus 18, and minus 18 added down to minus 1 is minus 19.
Oh, okay, ma'am. Thank you.
And 12 plus 2 is 14, and that's something I don't like. Let me check the minus 18. Perhaps I made a mistake there. So minus 3 times minus 3 is 9, and 9 added to 5 is, yes, this one is wrong. This one is wrong. So actually I'm adding the first row times minus 3 down to the second row. Minus 3 times minus 3 is 9. Added down to 5 is 14. Mm-hmm. And similarly, we get 14 minus 3 times minus 4 is 12. 12 plus 2 is also 14. This is what I had to get. And now, of course, row 3 minus row 2, we have 1, 1, minus 1, 6, minus 3. We have 0. I can now change the coefficients. 1, minus 4, 19, minus 14. And in the last row now, I have 0, 0, 0, and 0. Everything disappears. Everything disappears. So in principle now, I have a bigger problem. I can eliminate one more number only. I can eliminate this. I can make a 0 there by adding the second row times minus 1 upwards, but I cannot eliminate the last two coefficients before the vertical line. I cannot do that. So I can say row 1 minus row 2, and now it becomes 1. 1 minus 1, 0. Minus 1 minus negative 4 is 3. 6 minus 19 is minus 13. And minus 3 minus negative 14 is plus 11. And the second row remains as it was. 0, 1, minus 4, 19, and minus 14, and then 0, 0, 0, 0, 0. So you see what happens now. I cannot get rid of 3 in the first row, because if I use the second row to do that, I will inevitably spoil the 0 in the first row. I cannot eliminate minus 4 in the second row, because if I do it using the first row, it will spoil the 0 in the second row. So this is where we stop. And in this case, what we actually will do, we will choose 2 new variables. We will say x3 is let x3 be equal to sum A, and let x4 to be equal to sum B. Again, random constants. Now, if we choose x3 and x4 to be any odd numbers we like, then the x1 and x2 from the first and second equation could be expressed. In other words, I would get x plus 3a minus 13b equals 11, and in the second row, x1, and in the second row, x2 minus 4a plus 19b equals minus 14. So in principle, I can have the general solution like this. So x1 would be 11 minus 3a plus 13b. x2 would be, let's see, okay, all right, minus 14 plus 4a minus 19b. And then x3 is simply a, and x4 is simply b. And this would be my general solution. Instead of one constant, as in the first case, here we have 2 constants to be chosen. We can choose 2 constants, and then using these 2, we can express the other variables, the remaining variables. So the problem with this is, now how do we know whether to choose one variable and say, let the last one be C? Or maybe we choose two variables, two random numbers, and express the rest. Or maybe we can choose three. So how do we know that? That's the next problem. That's the next question. Let's try to solve that. Let me see if I have something for this still remaining. Yes, I have. Yes, this is exactly this. This is what I actually did. This is actually what I did. So the general solution, there we go. And then when we choose whatever numbers for A and B, we can express particular solutions. For example, I could say particular solution if, let's suppose, A is 3 and B is 1, then I have 11 minus 9 is 2, 2 plus 13 is 15, and minus 14 plus 12 is minus 2, minus 2 minus 11 is minus 21, for example. That's an example of a particular solution. As I said, it depends on what I choose for A and B, and I can choose them whatever I like, any real number. So the whole thing is now, if I get a row, all zeros, I still try to make leading coefficients 1 and zeros above those ones. Zeros always above ones. So it might be a bigger system. We might have 4 equations with 4 variables. So it would be more work, a longer thing. In this case, we clearly don't have a square system. We have more variables than there are equations. So if this system is not contradictory, if it is consistent, then it will have infinitely many solutions. In this case, it just happened that we got the last row equal to all zeros. But what could have happened is we might have had a number there. So it is possible to get 1, 1, 1 in all 3 rows. In that case, I would say if I have 1 here and then something else there, whatever, something, I would say I only need to choose that last variable, because using this last variable, I could express this one. And then using both of those, I could express the second row and the first row. So it all depends on basically how many non-zero rows we have. If I just had a situation where I had this 1 in the last row as well, and then I would have some number, whatever number x, not x, but whatever number, then I could say it's enough to choose this 1 variable to be something, some constant, and I could express the rest. So how do we tell? How do we know this? Clearing and moving on. So we are down to the idea of rank of matrix, the rank of matrix. So first of all, we have 2 definitions. Linear dependence, we already have had it earlier in the determinant. Linearly dependent. Linear dependence means that one row could be expressed using numbers times other rows. So it could be, for example, row. Okay, that's wrong. I didn't have to do. I didn't want to do it. Didn't plan it. So we would say, for example, row 3 equals minus 4 times row 2. That means that these 2 rows are linearly dependent. And then this simply means that I can eliminate row 3 using row 2, right? Because if I multiply row 2 by 4, add it down to this row 3, I will eliminate it. That's why we are interested in these linearly dependent things, or a linear combination of 2 or more other rows. That would be adding down 2 or 3 rows multiplied by numbers. So linear dependence means I can eliminate 1 row using others. And the rank of the matrix is defined as the maximum number of linearly independent rows. Maximum number of linearly independent rows. So what does that mean in practice? Definitions are empty if we don't know how to use them, what to do about the practice thing. And the thing is that basically what we need to do is we have to do Gauss method. We have to make the reduced row echelon form, or at least simply row echelon form. If we change the matrix into row echelon form, then the linearly independent rows are the ones that remain, the non-zero rows. So in principle, the rank of a matrix is the maximum number of non-zero rows that we can have after we eliminate everything else using Gauss method. So finding the rank of matrix in principle means apply Gauss transformations until you get the 0 rows at the bottom and you cannot get any more 0 rows. Then the non-zero rows, the number of non-zero rows will give you the rank of matrix. So generally the rank of matrix is hidden. In this matrix, for example, I don't know what the rank of this matrix is if I just look at the matrix. So what I do is, of course, I try to transform it using Gauss transformations. So that would be, so I'm writing equivalent. It's not equal. Matrices cannot be equal. Remember, matrices are equal only if the corresponding elements are identical. So I'm not talking equal matrices. I'm talking equivalent matrices in the sense of rank. Not equal. I cannot write it's the same. It's not the same. Matrix equality means term by term, everything.
If I put equal sign in the exam, will I lose mark?
If it's an accident, generally no. Unless you start using this equality. If you start using this equality deliberately and finding identical elements or something, then of course. But in this case, basically no, because what matters is the transformation. But since you ask, I'm sure you will not, because you now have paid attention to this idea, so you will do it correctly, I'm sure. All right, so the second row is second row plus 2 row 1. To make a 0 instead of 2, minus 2. And third row will be subtracting 3 row 1. And so we have 1, 2, 1. In this case, I'm not solving a system. In this case, I only want to see what the rank of the matrix A is. That's the only thing. That's why I'm using Gauss method. So 1 times 2 plus minus 2 is 0. 2 times 2, 4, and minus 3 is 1. 2 times 1 is 2, plus 1 is 3. 1 times minus 3 is minus 3 plus 3 is 0. 2 times minus 3, minus 6. Minus 6 plus 5 going down is minus 1. 1 times minus 3 is minus 3, added to 0 is minus 3, and now row 3 plus row 2 will give me a 0 row. And we see that we have row echelon form. Because we have this echelon, every leading coefficient is behind the previous one. So 1 in the second row is to the right, and below 1 in the first row we have 0. So this is the echelon form. This is the echelon form of a matrix. So it could be, sometimes it could look like this, many zeros and then something and something and something. So like an echelon pulling the cars, then an engine pulling the cargo train, everything follows behind. Reducing means making those extra zeros and ones. But in this case, we see again that we might eliminate 2, 1, perhaps either 2 or 1, but we cannot eliminate more rows. Rows will not be eliminated, because I cannot eliminate first row using the second row because the 1 stays no matter what, and I cannot eliminate the second row using the first row because if I try to do that, I spoil my zero. So this means that there are two rows that are not zeros. So I will say that the rank of this matrix is 2 non-zero rows. So in principle, when we solve systems of equations using Gauss method, you don't have to do anything extra. When you have performed Gauss method and arrived at the last possible transformation, you see the rank of the matrix. The rank of the matrix is the number of non-zero rows. Now let's see how to move on. So how do we use rank of matrix for this? Solve these systems. So let's suppose that the system matrix is A. Now we are back to systems. The previous example was simply demonstrating how to find row. And you saw that this is actually exactly the same thing we already are doing in Gauss method. And now, if we have the system matrix A, if we have the augmented system matrix A prime, and number of variables. So in normal cases, when we had system matrix, the system matrix has the same rank as the augmented matrix and the same number as the variable number of variables. So basically that means that if I have n variables, say 3, and the rank of the augmented matrix is also 3, so that means I basically have 3 rows that are not 0 rows. In principle, it might be the identity matrix after all. And the number of variables is exactly the same. And then the augmented matrix, of course, has to have the same rank. It cannot have a rank less than this, because the maximum number of non-zero rows, we already have these non-zero rows. It would be this situation. This means there is a unique solution. A unique solution, one and only one, it means. Unique means one and only one solution. If the rank of the system matrix, this one, is the same as the rank of the complete augmented matrix. And of course, the number of variables is the same. In other words, we see that the system matrix is a square system matrix. And also we see that there are evidently no 0 rows, or maybe if there are 0 rows, then they are somewhere else, then they are below, perhaps unnecessary. But in principle, we have a square system matrix, non-zero rows after all these transformations, so the determinant would not be 0 of this. So there is this unique solution if all numbers are the same, including the number of variables. If, however, the rank of the system matrix and the augmented matrix is the same, but the number of variables is greater, which means I have not a square matrix, but something like this. For example, this is the rank, and this is the number n of variables, of unknowns. And then we have these extra numbers, extra elements, right? The rank is the same. I'm simply writing the non-zero rows. The rank of both is the same. So solutions exist, but the number of variables is too great. This means we have infinitely many solutions. Infinitely many solutions in this case. And then finally, if the system matrix rank is less than the rank of the augmented matrix. In other words, I have the system matrix, it has some rank. And then, so the remaining rows might be zeros. But then we find the augmented matrix, and its rank is greater. It simply means that some of the rows that were zeros in the system matrix gain another non-zero number in the augmented matrix. And this means there are no solutions. So we can say that a system has any solutions only if the rank of the system matrix and the augmented matrix is exactly the same. If the number of variables, the unknowns, is also the same, then we have one and only one solution, unique one solution. If the rank is less than the number of unknowns, then we have infinitely many solutions. And another thing is the number of constants chosen at random, number of constants to choose, is actually rank minus n. That is, in the previous case, we had 4 unknowns, n, 4 variables, right? N was 4, x1, x2, x3, x4. But after those transformations, we got the rank of the matrix and the augmented matrix, only 2. So we actually see not r minus n, but n minus r. Evidently, I wrote it wrong, n minus r, because rank is less. Rank can be greater. And then we see that 4 minus 2 is 2, and that is the number of the constants. We had to choose a and b. That's why I said we need a and b constants there. The number of variables, the number of unknowns was 4, x1, x2, x3, x4. The rank of the matrix was only 2 rows that we could use. So it seems that there are 2 extra variables, and that means we have 4 minus 2, these 2 constants to be chosen as we like. So this is how rank of a matrix tells us a lot about the situation. In principle, when we apply Gauss method, rank of the matrix shows up automatically, as I said. You don't have to do it specifically. The only thing you have to do is, when you have simplified the system according to Gauss method, as much as possible, have a look at the ranks. And it will tell you, for example, the number of constants to choose. I do have examples. We have about 5 minutes. Let's see, what about those examples? Okay. So this is exercise 6A, number 2. It's simply for solving a system by Gauss method. This particular system has a unique solution using Gauss method. This should have a unique solution. So in principle, you would get the identity matrix, and on the right hand side, some numbers. So this is something that is possible to solve. I am more concerned with the other situations. And this is one. Now let's have a look at this. We can simplify. So of course, we could do it normally using x and y. But let's have a look. 6. Let's have a look at the matrix. 6 minus 4 minus 8 minus 15, 10, 20. This, first of all, can be simplified. The first row can be divided by 2. So we have 3 minus 2 minus 4. The second row can be divided by, let's say, 5. So we have minus 3, 2, 4. And now when we subtract row 2 minus row 1, we have 3 minus 2 minus 4, and we have 0, 0, 0. So what does this mean? The rank of the matrix A is 1, because there's only one row consisting of non-zeros. So the rank of the system matrix is determined by this row. The rank of the augmented matrix, the full matrix, well, if we look at the full matrix, the rank is also 1. But the number of variables is 2. So 2 minus 1 is 1. Of course, there's one possible constant to choose. So let's say it doesn't matter which. It looks like y is better to choose. So perhaps let y be some number c. And then 3x minus 2c is minus 4. 3x is 2c minus 4. And x is 2c minus 4 divided by 3. So we have the general solution, 2c minus 4 over 3 and c. And then depending on what c value we choose, we can get the answer, the specific solution for x and y. In this case, if we have 2 by 2, there is not much need to do the full Gauss method, to do the reduced row echelon form, because it is very simple, very easy to assume that one of these variables is some constant, put it into the one and only equation remaining, and express the other variable. So for 2 by 2, this part is okay if you don't do it in matrix mode. This part, because it's just as simple. So we could see that in simple cases we might have rank of matrix 1 and number of variables 2, or it could be that we have 3 variables, then we could choose perhaps 2. So it's possible to have another shape of the system. I could have 2 equations, 3 variables. So judging by this value, this r minus n or n minus r, actually, you see how many variables to choose freely and express the rest. And probably something else. Let's see. Okay, I want to do this one. Yes, I want to do this one because it is 4 by 4, like a big one. 4 by 4. That's one I wanted to do. Because this is the last lecture about linear algebra, I'm reminding you that we have a unit test on Friday. I will put in Ortus the testing groups. You have to come online on time. There will be 3 testing groups and no lecture on Friday because evidently testing 70 people takes a lot of time. I can't do everything at once. And I want to remind you, please practice. I know some of you will say, oh no, that's not possible. I cannot set my computer so that blah, blah, blah. It is possible. It just takes a little bit of work and time and adjustment. So practice and do it in advance. During any test, I need to see your head and your hands as you work, so that we do not have problems with academic honesty. And so, back to this last example. 5, 1, minus 2, 3, 1, 1, minus 1, minus 1, minus 1, minus 3, 8, minus 2, minus 5, and 0 instead of x4, minus 8, 3, 3, now 0 for x3, and 5 for x4, and 7. So paying attention to what is missing in the shorter equations. What is it that is missing? And so there's, of course, a lot of work we can do. So we can have 1, minus 1, minus 1, minus 1, minus 3 remaining, just exchanging the first row and the second row. 3, 1, then we have 8, minus 2, minus 5, 0, minus 8. Then we have 3, 3, 0, 5, 7. Then we create zeros below 1. So 1, minus 1, minus 1, minus 1, minus 3. Now let's see. Row 2 minus row 5, row 1, 0. 1 minus 5 is minus 4. Minus 5 times minus 1, 5 plus minus 2 is 3. 5 plus 3 is 8. 15 plus 1 is 16. Now here we have, okay, minus 8. 0. 8 and minus 2 is 6. 8 and minus 5 is 3, 8 and 0 is 8, and 24 minus 8 is 16. Okay, something went wrong here evidently, because I think there had to be, no, not yet. Next one, 0, so now times minus 3, 3 minus 3 is 0, minus 3 times minus 1 is plus 3, we have 6, minus 3 times minus 1 is 3, we have 3, minus 3 times minus 1 is 3 plus 5, we have 8, this is where we have it, and minus 3 times minus 3 is 9, plus 7 is 16. Aha, see what happens, This row disappears. So in the next transformation, we would have 1 minus 1 minus 1 minus 1 minus 3. We would have 0 minus 4 minus 3, 8, 16, 0, 6, 3, 8, 16, and 0, 0, 0, 0, 0. So we already see that the rank is, let's say, maximum 3, minimum 2, because we see that the row 2 and row 3 cannot disappear completely, they cannot eliminate each other completely, but they can be simplified a little bit. So we already see here that the rank is minimum 2, maximum 3, and we need to figure out which it is. So we could, for example, try to, let's just divide the second row by minus 4 to simplify things faster. Why that? Because I want 1 in this place. So I divide the second row by minus 4. So I have 3 over 4. I have 8 divided by minus 4 is minus 2. And 16 divided by minus 4 is minus 4. Last row is all zeros, and the third row, I could divide everything by, perhaps I could divide by 6, or I could simply say now I will take this row, multiply by minus 6, and add it down to this third row. To make things faster, you can do things more gradually, more slowly, in any way that's better understandable to you. I'm just trying to do it as quickly as I can. So we have 0. Now I have 1 times minus 6. Added down will be 0 here. Now I have 3/4 times minus 6 is minus 18 over 4 is minus 9/2. That's minus 4.5. Added down to 3 is minus 1.5. Minus 2 times minus 6 is 12. Added down to 8 is 20. Minus 4 times minus 6 is 24. Added down to 16 is 40. So in this case, we see now we have this perfect echelon form. We might divide also by minus 1.5, but at this moment, I will not do things to the end. What we see is the rank of the system matrix and of the augmented matrix. Both of them are equal to 3, but the number of variables is 4. So we only choose one random constant, and it's already obvious that we should choose the last x4 to be some random constant, and then we will be able to express the rest using this random constant. That's the main idea about the rank, which is why I actually wanted to do this exercise. If necessary, on Wednesday, I will redo this or something similar. We may go through one more example of these. I don't have any objections. That would be quite normal. So please get ready for Friday, do your homework, upload your homework to assignment. So learn to find the assignment in Ortus, learn to find how to upload. That's by doing the homework, for example. Make sure you know how to do it, where to do it, even if you don't do it yet. Because on Friday, as you write the test, I already said there will be 40 minutes for the test, 3 systems of equations. I can already tell you that. The first one will be Cramer's rule. The second one will be inverse matrix. Inverse matrix method for system. And the third one will be Gauss. It will be Gauss method. You will have to investigate the situation using Gauss method and see, does the system have one solution, no solutions, or infinitely many solutions? So there will be three systems, each one with a different method. And that's it. 40 minutes, and then after that, 10 minutes to prepare the file and upload to the assignment in Ortus. The assignment for homework, for home assignment in Ortus is already open. So this is where you can practice, that you know how to find it, you know where to look for it, you know how to look it up, you can search for your assignments, so that there are no questions at all about how to hand in the work. All right. On Wednesday, I will repeat things about the test. Evidently, they need to be repeated, because on Friday, no matter how many times I repeat, there will still be some people who have no idea, no clue whatever, what to do and how to do things. So please practice, find things in advance, where to do things, how to do things, and get ready for the linear algebra test by doing the homework. Because the homework, actually, if you do the homework, then everything is okay. Then you have prepared. Then you are ready for the test. That's all there is. All right, now I'll say goodbye because I have another.
But I have a question. So the exam, will we get the marks for the working? Like, if we didn't have the final answer right, but we did the working correct, will we get the mark?
Well, because there are only 3 questions, I will see. So sometimes some arithmetical mistake happens. I know that, and of course, I will take that into account if you understand the method. However, for example, in Cramer's rule, if you do all 4 determinants wrong, then evidently something is using your results, but evidently not if everything goes on being wrong. Link of this meeting in Ortus. The link is in Ortus all the time. The link is in Ortus all the time. So who's asking? Somebody who came late. I don't want to put this in Ortus, but if you email, I will send you the link. Generally, if somebody emails me, I send the link. I don't want to put them in Ortus because that means that people will stop attending lectures and only using the recorded lectures, and that's not the thing. You are full-time students, you're supposed to attend lectures. So yes, in individual cases, I can send the link to the recording, but I'm not going to put them online publicly, because that would stop many people from attending. Okay, then, I think it's time to finish. I have another meeting in just a few minutes, so I'll say goodbye to you and see you Wednesday morning early. And for elementary mathematics, those who did ignore the elementary mathematics introductory test are added to the course automatically.
Thank you so much.
Okay, welcome, goodbye.
Thank you.
Thank you, ma'am. Have a nice day.